So in my infinite wisdom, I showed this presentation to my younger daughter. She's 10 years old. And she looked at the cloud storage acceleration layer and she said, Daddy, cloud storage makes no sense. You're going to lose everything after it rains. I am yet to convince her. So maybe you can give me some clue at the end of this presentation what I can tell her to make her believe I won't lose the data. All right, so for this portion of the presentation, I'm going to start by talking about the TCO benefits of our hyperdense QLC P5336 61.44 terabyte QLC drive. And really the motivating problem for us software guys and solution guys is how to expand the reach of this QLC to more use cases, more customers. And the solution is creating an easy button with cloud storage acceleration layer and a reference storage platform. So we have a demo as part of this presentation where we put together our P5810, the newly the SSD that we're launching today, with our newly launched QLC hyperdense 61.44 terabyte drive. We put both of these together with CSAL in a storage node, and then we look at the TCO and performance advantage at the solution level, at the box level. And then we wrap up with a summary and a conclusion. So wide range of use cases and customers are adopting QLC. One example is Alibaba local disk use case. And what Alibaba did with their second generation big data local disk ECS instances is that they were using HDDs in that second generation local disk instances, and they couldn't scale it further in performance or capacity because of the power and space constraints that HDDs imposed. And HDDs obviously were also not scaling in performance. So what we did, we replaced the HDDs with QLC, and we doubled the performance and doubled the density. So so this enabled Alibaba to keep the price of their service constant, same, and double the performance to their customers. So quick iPhone analogy, new iPhone came out last week. The price of it is same as the last year's iPhone, 1,000, 1,100, depending on the model, and the performance is way better. So Alibaba did exactly that. They doubled the performance of their service, but held the price to their customers constant with the QLC. And really the density was the key here. Obviously, when you replace HDDs with QLC, the CapEx is going to be higher. But if you look at the OpEx and the rack tax, because we have higher density QLC, and this is the third generation QLC, which is a 16 terabyte drive, P5316. That's what they deployed at scale. And when you take those OpEx and rack tax savings, that's what basically kept the price same. But that's the density advantage. We doubled the density, kept the price same, and that's how they were able to achieve this same price for their third generation big data service.
On the same time, I imagine they were switching from fast backend drives over to NVMe, so they gained on the CPU reduction by not having to deal with that aspect of it.
Absolutely, absolutely. The HDDs were imposing a lot of bottlenecks. So you can see, you picked up on it that, yeah, they require less CPU now because the IO weight and all those other issues are gone.
Exactly.
Yeah, exactly. So they can fit two of their largest instances in the same box that previously they were only host one local disk instance. Okay, so then, we got two things out of this deeper collaboration with Alibaba. One, obviously, it's a great proof point how QLC can replace HDDs, or higher density NAND can replace HDDs. The second thing we got out of this collaboration is this cloud storage acceleration layer. We co-developed this cloud storage acceleration layer with them. But Alibaba uses Optane SSDs, and Optane is still winding down. They continue to use Optane SSDs. But obviously, we are talking about here expanding the reach of our hyperdense QLC. This is previous generation QLC in this use case. Hyperdense QLC, we want to expand the reach to more use cases, more customers, and we need an Optane replacement. So this is precisely what we have engineered here with P5810. So we analyzed various use cases, particularly the CDN and big data use case, which is the Optane plus QLC deployment. And we looked at the Optane profile. What kind of characteristics workloads actually demand versus what Optane is supplying, right? So we're comparing two of the most important metrics here. So we looked at these use cases and determined that 37 drive writes per day is the absolute worst case endurance demand these workloads impose. And Optane was supplying 100 drive writes per day. So we right-sized our P5810 to be 50 drive writes per day. And the other important metric that Ratnesh mentioned is the random 4K write performance. Now, we determined the demand per virtual disk. This is like, I have the explanation why it's so low, 8,000. What are you talking about? The SLC drive has 500K IOPS, or Optane had 1.5 million random write 4K IOPS capability, but we're talking about this 8K as per virtual drive, and I will explain it shortly. Optane was able to supply about, demand is 8K, Optane was able to supply about 20K, and we have, again, right-sized our QLC to be about 10K IOPS per virtual drive. So now let me explain a little bit about basically why these 8K, where these numbers are coming from. So this workload, 4K random write workload, is on top of our software, cloud storage acceleration layer. We present a coherent 4K block, good old 4K block interface on top end of the cloud storage acceleration layer library. And on the bottom, what we do is we land all the 4K random writes in the arrival order on this cache, SLC cache. We will just place them in the SLC cache. And any hot data, any data that gets overwritten, all that churn will happen in the SLC tier. And endurance burn will be from the SLC tier. And then what is the long-term data, we will move that from SLC to QLC in a very NAND-friendly manner. We will move it sequentially, we'll write so the write amplification factor is contained and mitigated. We will write in that large granularity, in the IU granularity, so we don't take that read, modify, write penalty, etc. So at the bottom, what is SLC bandwidth consumption? SLC bandwidth consumption is, okay, the workload that is underneath the CSAL is actually a mix of random and sequential writes. And where are the random writes coming from? 75% of those random writes are actually coming from our logical to physical mapping table adjustment. So CSAL itself is an FTL, a flash translation layer that runs in the host. And we run basically, the way we run it is there are multiple instances of cloud storage acceleration layer that will run. Each cloud CSAL instance will run on a single virtual CPU. Single virtual CPU, it will bind to one Optane and one QLC drive, or one SLC and one QLC drive, and then expose multiple virtual drives. And this performance up over there is just from one virtual drive. And it is the performance after taking out all of the work that CSAL is doing, especially the logical to physical mapping table work, which I will talk about in the next slide. Okay. So to summarize a little bit this slide, and maybe I will pause after that for questions. So we all worked on Optane SSDs, and it was an awesome technology, but unfortunately it is gone. I'm still sad about it, but I'm excited that we have actually created P5810 after putting all those learnings we got from P5800X Optane, learning the use cases Optane and QLC, and then providing you a better cost, performance, endurance fit to those use cases with our P5810. We really didn't over-engineer it. We just right-size engineered it to match the demand and match the workloads to provide that better cost, performance, endurance profile. Okay, maybe I'll pause here for any questions you may have.
You mentioned the CSAL is a host layer integration. So something in the operating system, Linux versions, Windows versions, hypervisor version?
So it is an SPDK. It's a user space storage performance development kit component. So it runs within the SPDK. It's an FTL inside SPDK.
Okay, so this isn't something you aren't exposing to your end users as a general purpose tool.
Say that one more.
That wouldn't be something they would just go and download. You'd be exposing this as part of a package to come with the systems integrated correctly.
Correct. Okay. And you will see one deployment that we have coming up. Yeah. Any other questions?
The worst case use case demands where you're testing, where you said, just said based on your internal analysis. I mean, how are you because you're having to simulate like user workloads, right?
So we got field data from real deployments, Optane plus QLC deployments, and we looked at that data for CDN and big data workload.
So when you went back to the Alibaba use case, that was an Optane and QLC drive in the past, and you made a change to your SLC drive?
No, they're still using Optane. They're still using Optane. We are just launching SLC today, right? So obviously, yeah.
But in the prior iteration, it was disk drives rather than QLC? Is that?
In the prior iteration at Alibaba local disk service, their Gen 2 was hard drives, and they replaced that in the Gen 3 big data service. They are replacing that with they replaced that with Optane plus QLC. Yes. Let's go to the next slide. So now we have our hyperdense QLC. The third generation QLC that was deployed in Alibaba use case is P5310. That's the third generation QLC, 16 terabyte, 64K IU. Now we're going 4x more density. That's we're calling it hyperdense, 61.44 terabyte drive. We launched this. Today we are launching P5810 that will replace Optane. So what I did was I just simply in this table compared the TCO, back of the envelope calculation, TCO. It took into account the CapEx, the OpEx, the rack tax, and all that. And we see that once you replace Optane plus QLC with SLC plus hyperdense QLC, if you replace that, you will straight up get 2.5x TCO advantage. And to give you a sense of this, hypothetically, if you roll all the CapEx, OpEx, and rack tax numbers into a single number, and you have a storage node basically. Let's say that storage node is the metric that we are representing is $1 per gigabyte. With O plus Q, you'll spend about 20 cents per gigabyte. If you amortize 5 years cost, OpEx, CapEx, everything, 20 cents a gigabyte, and you will get with this 8 cents a gigabyte. So obviously, this is a huge TCO savings, and hyperscalers and large customers know about this. They're rapidly changing their stacks and whatever else they need to change in their infra to take advantage of this hyperdense NAND. But our, again, motivating problem for us is how to make it available to everyone, right? Extend that to everyone, right? So part of the answer is CSAL and our reference storage platform. So first I'm going to talk about the cloud storage acceleration layer, then a reference storage platform. So let's get into what is cloud storage acceleration layer. So it's a open source library that is a BDEV in like tech geek jargon. It's a BDEV, a block device abstraction inside SPDK, Storage Performance Development Kit. Now, let me just up level and just explain what it does with a performance pipe metaphor. So you know how NAND has a read performance pipe that is already very big. But the write performance pipe in NAND is narrower. And as we get denser and cheaper with going from TLC to QLC, that write pipe is the one that gets narrower and narrower. What CSAL tries to do is make that write pipe bigger. And the way it does it is it solves that write amplification. It controls that write amplification factor, which is the root cause of that pipe getting narrower. So that's essentially at high level what it does. So how does it do that? We use the term write shaping. That's what we do, write shaping, right? So what is write shaping? Write shaping at a very high level is, okay, writes come and they always get, we land them on SLC drive. And any short lifetime writes are just staying and churning and burning SLC, which has 50 drive writes per day, pretty good endurance, pretty good performance, etc. So these files that get written and deleted, they will never be going to QLC and burning endurance there. They will just stay in SLC. And when we do have to move things from SLC tier to QLC tier, we basically move them in a very sequential manner. So there are three, let me just one click down on why you need write shaping as we are heading into this hyperdense NAND world. So 3 reasons. One, I think you asked that question. As the NAND is getting denser and cheaper, the IU size is going to get bigger. And the reason is, Roger mentioned that, the DRAM, the power profiles, etc., the DRAM you will need to have that logical to physical mapping table, the lookup table, is going to get bigger and bigger. So to optimize for that DRAM inside the SSD, you need to have larger and larger IU. And this kind of write shaping mitigates that read modify write penalty that comes with large IU drives, that if host writes 4K, you're still writing 16K kind of penalty. So it eliminates the read modify write penalty. That's number 1 reason for using write shaping. The second reason is the new emerging interfaces are coming, zoned namespace and flexible data placement. Those are zoned namespace, ZNS, and FDP. ZNS, we have a quick case study in the next slide, I think. ZNS requires hosts to write strictly sequentially. And they allow some data placement capability that will help with mitigating that write amplification factor. But host has a constraint, host must write sequentially. So that is another write shaping that CSAL is able to provide. And third one is flexible data placement. Google and Meta have defined yet another different data placement technology interface that is called flexible data placement, and that also requires a smart FTL running in the host, and CSAL basically becomes that smart FTL. So those are the 3 reasons: ZNS, FDP, these emerging interfaces, and the large IU or larger to avoid the read modified write penalty. Now, this is basically a slide that shows how actually CSAL uses SLC. So kind of Ratnesh mentioned there are 3 use cases and how intelligently we place things, etc. I just wanted to give you that there are 3 regions. We divvy up the SLC drive into 3 regions. The first region is the cache region. That's where all the user writes sequentially land, and we basically use that cache region for that. And then logical to physical mapping table. So we are an FTL. We have to keep 4K indirection unit at our level. And we provide 4K indirection unit. But instead of using DRAM all the way, we use paged logical to physical mapping table. So that saves DRAM. We basically page in and page out to a portion of the SLC drive, so we don't have to use. So for example, if we have a 128 terabyte capacity behind CSAL, we would need 128 gigabytes of DRAM. If you take 4 bytes per sector, it'll basically be 0.1%. So it's for 128 terabyte, you need 128 gigabyte. That's a lot of DRAM. So instead of using 128 gigabytes of DRAM, we'll use something like 10 gigabytes of DRAM and then page in, page out to SLC. So essentially, SLC saves us DRAM cost through this paging algorithm that we have, or swap algorithm we have implemented in CSAL. Lastly, this is in response to my daughter. Okay, we have this CSAL is an FTL that is crash consistent and power fail safe. So we save the metadata. We obviously need to save the metadata to make sure our FTL is power fail safe and crash consistent. That metadata also goes on our SLC drive, in a region of the SLC drive.
For this L2P region, does the system vendor have to do something on his board design, in his BIOS, something like this? It's just I plug in the components?
Yeah, all you need to plug in is
software and everything.
Everything is, you need to plug in SLC drive. Our software will simply use, carve it out and start using it. 3 regions. All right. So just quickly, since last year, a lot happened to cloud storage acceleration layer. We were originally part of Intel, And we actually open sourced it last September in the SPDK release version 22.09. And then Optane wound down happened, and CSAL was end of lifing there. Solidigm knew about it. Solidigm knew that it was crucial for our relationship with Alibaba, as well as for QLC expanding the reach to more use cases, more customers, etc. So we were acquired by Solidigm team in February of 2023. As soon as we joined, first thing we worked on was establishing SLC product, P5810, making sure we understood what the requirements of these Optane plus QLC use cases was, and making sure that we land our P5810 correctly in terms of attributes. And then, I don't know, Ratnesh, you talked about it, but one of the things we wanted to make sure was we didn't make our SLC SSD very complex. And there is a capability called VSS, variable sector size. So the sector is like a small additional bytes at the end of the sector where we could put our crumbs, metadata, so we are power fail safe, crash consistent, etc. So what we did was we changed CSAL algorithms so SLC didn't need to carry. Optane had it, Optane SSD had it, and we relied on it. CSAL relied on that capability to make it power fail safe and crash consistent. So we changed our CSAL algorithms. All the patches are also upstreamed. They're getting integrated into the mainstream as we speak. But we basically mitigated for VSS. We no longer rely on VSS capability. So on our SLC drive, we don't need to carry VSS. We're also working on RAID and ZNS FDP readiness. These are new emerging interfaces for data placement, control, etc. So let's look at how, in little bit more detail. Yes, please go ahead.
ZNS FDP?
So you can think of them as zone namespace. ZNS stands for zone namespace, and FDP stands for flexible data placement. These are two new emerging interfaces that actually allow host to maybe control the placement of data, so the right amplification factor is mitigated or controlled.
Well, once you actually said the words, I understood what you.
All right.
Don't
Yeah.
see the acronyms very
Yeah.
often.
But isn't the new SEF that they were talking, or SEF, whatever you want, I can't call it SEF.
Yeah, I know.
Already SEF. But isn't that supposed to be the evolution of both of those things? Is that part of your focus as well?
No, we're working on this flexible data placement and ZNS more right now. That's not standardized and not yet. Yeah, so I'm not really sure about that. I'm not totally ramped up on that technology yet.
Gotcha.
And so the RAID 5F is a flash version of RAID 5, is that?
I will get to that in the next slide. That's perfect segue here. So, okay. So first how P5810 enables this CSAL's core capabilities to ultimately achieve the goal of expanding those QLC benefits. Let's talk about right shaping is first one, right? So we're mitigating the DRAM footprint by having this SLC as the L2P, all the, we talked about. We also have these emerging interfaces like zone namespace and flexible data placement. We will do right shaping for those. But then there is another benefit here that I alluded to before, caching. So if you have a very high temporal locality based workload that you write and overwrite again, or you write and delete, in these cases, like I said, caching is appropriate setup. So we have this tiered architecture, which is great. So here I have a synthetic workload, 64K random write with a Zipfian theta of 1.2, which means roughly 95% of the accesses are happening to 5% popular LBAs. It's like five songs out of like 100 songs you're always playing kind of thing. So you have those hot LBAs, and 95% of the accesses are hitting those. And in that kind of temporal locality based workload, you will get 2x the performance gain over TLC with S plus Q, with SLC plus QLC, because most of the response is coming from SLC, and it's great performer. All right, so next one is the RAID 5F. So 5F, it's RAID 5, but it's a full stripe RAID 5. So the traditional RAID 5 or any parity RAID is a read, modify, write RAID. Meaning, if you're doing a small write, you have to do read. You have to do 2 reads and 2 writes. Read old data, read old parity, XOR them together, write new data, write new parity. Every small write becomes like that. It's again a read, modify, write penalty. And because we have SLC tier, we can always play full stripes downstream. And it also tremendously simplifies the implementation of RAID 5 or any parity RAID. There is more that this is 2x. Just if you look at the full stripe RAID 5 formula and partial strip update RAID 5 formula, you get 2x straight up benefit. There is also parity RAID suffer from another problem called write hole. And to close that write hole, you have to do additional logging writes. And that basically translates to 2 to 3x benefit of implementing this full stripe RAID 5. And it's like another version of large IU because from SLC tier, if power fail happens, your stripes are inconsistent, it doesn't matter because we have SLC persistent tier to always replay those writes back to the bottom layer, to the RAID layer. So we don't need any additional things other than just implement a simplified version of RAID 5 or RAID 6. We call them RAID 5F and RAID 6X. Why are we doing RAID? Because these emerging interfaces that are coming up, the data placement SSDs like zone namespace and flexible data placement, certain configurations cannot carry XOR engine inside the SSD. XOR provides 2 to 3x the reliability. And when you drop that, you actually drop the reliability. So we are picking that back up here at the host FTL level, that RAID, to bolster that reliability again. That's the reason why we're doing RAID 5. Okay, CSAL and SPDK have ton of pooling capabilities, and you can chop things. You can create a big pool of this hyperdense QLC. You can chop it up into whatever size volumes and expose them out to cloud tenants. So you have that, and the way we'll do a case study or demo shortly here. It shows how we are disaggregating, and by doing that, we are able to improve our capacity and performance utilization. Lastly, CSAL already works with ZNS. Here is a Kubernetes cluster using CSAL to adapt ZNS drives to 4K, good old 4K block on top of CSAL. So we have basically, and we can trivially do data placement and tenant isolation. We have LBA ranges, but we simply expose a large pool with LBA ranges, and we know what LBA range a cloud tenant is hitting, and based on that, we can steer that traffic separately to those sets of zones or separate we place them in a separate island, so to speak, or where we place it on the NAND area is not overlapped with other tenants. So that we achieve this tenant isolation, which this blender effect or mixing of multiple tenant workloads leads to this WAF or write amplification factor, and we mitigate that write amplification factor in this particular example, 3.8 to 2.3.
Question?
Yes?
You're talking about RAID 5 there. So you lose a drive. These things are massive. What kind of rebuild time are you looking at?
So we looked at the rebuild times. It's still under a day, if that is the thumb rule. It's still under a day for NVMe SSDs. For HDDs, it takes forever, and this kind of large blast radius will be a concern. But I acknowledge, yes, as we get bigger and bigger, we have to solve this problem. But for 61.44 terabyte drive, it's still falling within the realm of, okay, this is still manageable. Rebuild times are not increasing that much still.
Any thoughts of going to RAID 6?
We are thinking about that, absolutely, yes.
Does the full stripe help? Full stripe size help that?
No, when it fails, we still have to rebuild. Yeah, we still have to rebuild.
Sorry, a question as well. So we talked a bit about RAID 5 here, and just to kind of take a step back. So in terms of CSAL's application, I presume this is very much just for software-defined storage. We haven't got any kind of integrations with any, hardware RAID controllers, storage vendors, that kind of thing.
So you can put CSAL as a flash translation or cache layer on top of any RAID. You can have a read modify write RAID, traditional RAID, MD RAID, and we can always play full stripes, and we can provide that write hole closure for free, basically. Yes, you can plug it in with any RAID, but we are building a full stripe RAID as part of the open source. But I know of some vendors using CSAL underneath some kind of hardware RAID and such, or MD RAID in Linux kernel.
Because my kind of follow-up point to that as well was that, you know, if we're talking about landing these writes on the SLC storage, well then it's still going to be necessary to make sure we've got some element of write redundancy, that if the drive were to fail before it's been tiered off, well then that could be data loss. So I was just wondering where we can get that redundancy, whether that's defined in software, whether that is, you know, passing off to RAID controller, software defined storage, that kind of thing.
Yeah. So some deployments, this is a great question. Some deployments are cloud native apps which have redundancy built in. If, for example, if I go back to Alibaba use case, that's a local disk use case where the cloud native apps like Hadoop, Spark, etc., are sitting on top of these cluster of these kinds of nodes. So they don't need any redundancy, any RAID. But for the specific deployments that you might be thinking of, we would do RAID 1 of SLC and RAID 5 will pair up like that to make sure that SLC doesn't become a single point of failure, so to speak.
So just so I'm completely clear on this one, so we would RAID 1 the SLC and then present it into CSAL?
The CSAL will underneath it use the two SLC drives as RAID 1, and CSAL will abstract that all away from you. All the RAID is underneath the CSAL. So CSAL will present a very consistent 4K block device on top. So you will see a single block device. You won't know all these nuances of RAID 1 the SLC, RAID 5 the TLC. You'll see a large pool of QLC basically.
So when I was thinking of the hierarchy, I was thinking, okay, well, I'm going to see a virtual drive, logical drive, however you want to kind of frame it. I'll see that will be my CSAL drive effectively. That has then got its, you know, tiered QLC storage. That's got its performance SLC storage. And then that was the part I was just kind of missing there is, okay, is it that CSAL needs to be aware I've got these multiple SLCs and do RAID across them, or actually I need to configure RAID, pass that to CSAL and say, no, this is just my, you know, write tier. This is my capacity tier.
Yeah, so you will do this control plane configuration up front. But once you configure CSAL, it'll be a single logical device on top. The cache portion, the SLC portion will not be exposed. In the current deployments, we might consider exposing that if application is smart and wants to do something with it. But right now, SLC would be just consumed by CSAL. CSAL will only present the capacity of the QLC drive.
Thank you.
All right, so the bottom line here is that the CSAL has all the key abstractions to extend the high density QLC and adapt to also these new data placement emerging interfaces to 4K block interface. So you could have your legacy applications interface to these new and emerging SSDs, data placement SSDs without changing. That's one of the value props of CSAL as well. Large IU, etc. Right? So we mitigate, we do write shaping, etc. All right. So in addition to CSAL, we're taking a community-driven approach to. We're taking that next step in our solutions approach to create a reference storage platform. So why a reference storage platform? So open source building blocks are bag of parts. It's hard for us geeks to put together. Let alone if you're not tech savvy, it's really hard to assemble. And this hampers our rapid development, assessment, and deployment of storage technologies. And what we are doing with reference storage platform is we bring it together into a turnkey solution. So a car analogy, I'm an SSD vendor, I want to build tires. And I want to then say, okay, my tire in standalone looks like it's going to perform, it's going to have great TCO, but I don't have a way to actually tested at a solution level, at a car level. And this reference storage platform provides that ability or capability. So, and we are taking a community-driven approach. We have partners being very transparent and adopting. Other horizontal industry players can participate in this reference storage platform in the sense that, okay, as SSD vendor, I can bring capabilities like hyperdense QLC or P5810 and ZNS and FDP. And maybe a software vendor can bring compression algorithm and put it in that car-like solution, and that's going to bring the TCO down. And maybe platform vendors can bring, instead of building a x86-based storage nodes, we can build maybe IPU or DPU-based storage nodes. That may bring TCO further down. So as you add these capabilities as vertical lines, you will bring down that TCO at the solution level, is the idea. And most of these components are open source, standard components that we are putting here. But one partner, as an example, is bringing the high availability capability, and they don't want to open source that, and that's cool. They don't have to. They just use our standard components and build their differentiating capability, high availability capability on top. Starwind I'm talking about, we'll see in the next slide. But good news is that we already launched this one instantiation of this reference storage platform, and we demoed it. I'm going to show you that demo. We did it at FMS of 2023. I'll try to play that demo here. We have a recorded demo that I want to show you. Okay, so thanks to our partners, what we have is a disaggregated NVMe over Fabrics target. It's a TCP target. So you can think of it as a box that is the big SSD of the data center. It's the big SSD of the data center that we have built. And why is it a turnkey solution? Okay, we have built a container and a VM image. With one click of a button, you can download it to our two defined hardware platforms. Here is x86 based, one from Dell, one for standard OEMs, one from Dell, one from Supermicro. You download that container or a VM, boom, you have a working NVMe over Fabrics target. And now you can test, drive, or test your technology. Okay, next, in keeping with the ethos of eating our own dog food, we put our SLC, P5810 and QLC, P5336 hyperdense QLC drive into this solution and then see what kind of TCO benefits and performance we get. So here is a quick annotation of the demo. So unfortunately, the demo is not clear. These dashboards are visible, but the annotation I'm doing, okay, so top line on the dashboard you will about to see on the live recorded video is this read bandwidth and write bandwidth. So you can think of these big drives of the data center, and the clients are hitting this storage node with 70-30 workload. And there are multiple, we are exposing multiple volumes out of these. Each of these clients are hitting 70-30 workload to their own virtual drive and trying to saturate this whole box. So there's a lot of queue depth, a lot of workers on the clients trying to hit this single JBOF. And we are this NVMe over Fabrics target. So first line is read bandwidth and write bandwidth, 70-30. We kept it really simple, 70% reads, 30% writes, 7 plus 3, 10 gigabytes. That's your 80% of the saturation of our 100 gig NIC that is on this NVMe over Fabrics target. 100 gig NIC is able to deliver over TCP about 12 gigabytes per second. We're trying to make sure there is just, we saturate only 80% of that bandwidth. So in case of rebuilds and other things, that's how, it's like naturally how it is kept. So we do 80%. Second line here is the write amplification factor. So what kind of write amplification factor we are seeing on SLC drives, what kind of write amplification factor we are seeing on QLC drives and TLC drives, which is the comparison. And then last line is, okay, what kind of CPU utilization we are taking, what kind of network utilization we are taking, what kind of memory utilization we are, what kind of memory consumption we have, okay. So this is an A-B comparison. All right, so getting back to this A-B comparison. So we're comparing, in this table, we have two such big drives of the data center, NVMe over Fabrics target. They're single socket, 10 PCI slot Gen 4 servers. 10 slots, Gen 4. We plug in 10 TLC drives, A-B comparison. On A side, we plug in 10 TLC drives, And on B side, we do 3 plus 7, 10. 3 SLC drive and 7 of our hyperdense QLC drive. First row itself, you quickly notice 138 terabyte is all you get on the TLC side, 16 terabyte P5520 Solidigm drives. And with the hyperdense, you can get 344 terabyte. That's a pretty dense system. Now, if you look at the performance SLA, we're keeping it at 500 megabytes per second per virtual drive, and we are creating 16 terabyte virtual drives out of these two boxes. So you can create 8 performance units, 8 virtual drives out of TLC because it lacks density. But you can get 21 16 terabyte drives out of the QLC side. Okay, and this chart shows how density as a function of required performance. So really the required performance on x-axis, I'm limiting that to 500 megabytes per second per virtual drive, no more. So you may have surplus coming from TLC, but the goal is to saturate the network. So if you have any surplus performance, that's going to get left on the table on the TLC side. And you can only get 8 because of lack of density. So this is the comparison we're talking. So you can get 500 megabytes per second per virtual drive, no more. From each of the virtual drives, you have 21 units. Each of them will deliver 500 megabytes per second per virtual drive. And you get, you saturate the box at 80%, like we said. And here is the TCO comparison. So again, it's basically, you know how the TCO is calculated. Basically, on the TLC side, you have 8 virtual drives. And on the QLC side, you have 21 virtual drives. You have to pick up these boxes for the parity of the capacity and performance, SLA. You have to pick up these boxes, TLC boxes, 2.5x extra TLC boxes to gain parity at the capacity. That's how the comparison is done. And therefore, the space savings, cabling, extra at that large scale at the cluster level, you will end up getting the rack tax higher, OPEX higher, etc. And when you roll all that in, you get 35% compared to TLC now, you get 35% better TCO, conservatively speaking. Note that I will talk about in the demo. In the demo, we have this configuration knob you were asking about CSAL. We used all DRAM. We didn't use SLC in this particular configuration. We used all DRAM, logical to physical mapping table. So we used about 750 gigabytes of DRAM on the QLC side. Roll that in. Additional CSAL obviously takes CPU to run. There are multiple instances of CSAL running here. You will see the additional CPU utilization. Rolling all that in, you get about 35% TCO benefit. So from a big summary perspective, you have 2 large drives of the data center. Both deliver equal performance. But on the QLC side, you get 35% better TCO for the same performance. Okay. So now I'm going to go to the demo. You can see that we have 10x TLC P5520s on the left-hand side and 3x SLCs plus 7x QLCs on the right-hand side. Top row, we're pretty much saturating we're getting, this is your read, this is your write, you sum total it. That's your dashboard in the center that shows what the bandwidth coming out of this box is, big drive is. 10-ish, it's fluctuating here and there, but it's pretty much neck to neck. Then on the TLC side, you see that we have 2.77 write amplification factor. We're not running CSAL on the left-hand side. And on the right-hand side, CSAL becomes the FTL. It has a WAF of 2.34. And you look at the QLC WAF, it's 1. It's the best case because we write sequentially. We take that WAF at our FTL level. So QLC is 1, SLC is pretty much 1. Basically, it's drives are not basically drive level FTLs are not engaged here. Their write amplification factors are 1. So and then you can see that on the TLC side, because we are not running CSAL, the natural CPU consumption, the first dashboard at the bottom row is 28%. We take about 38%, 10% additional CPU utilization. On the extreme right bottom, you see 15 gigabytes versus whopping 743 gigabyte. That's because we are not doing tiering or paging yet. But We can do that. That's a configuration knob. We can change it. We can, depending on, you can do cost performance trade-off with that. But right now, this configuration, we're running 742 gigabytes of DRAM. We rolled in that number into the TCO calculation.
This is a logical next step. I'm just thinking one of your vendors is probably too soon because you're just coming out with the announcements. This would be a really good fit for the new vSAN enhanced storage architecture, which has gotten rid of the two-tier cache drive plus the storage drive. And what this sounds like is you could just slot it underneath and say, we'll give you back that performance, price performance equation by going to that, because otherwise it's too expensive to go for high performance with vSAN. And you're looking at pretty high risk because you're looking at really the minimum. I think the minimum is a 1 drive write per day, which are the TLCs that are not the most cost effective for this kind of high density storage system. So is this, can you say anything towards working with VMware on that front? Or could we just say that that's NDA for the moment?
I think
Maybe I'll defer to Roger. Or
I think we should probably set TBD on that one.
Yeah.
Okay.
I would say draw your own conclusions out of that.
Makes sense. I can work with that.
I mean, aside from the reference architectures, is there an iteration of this in the wild today, like something at an enterprise scale that I can go buy?
so
I mean, I get that the one drive, the new SLC drive is brand shiny and new, but CSAL has been around for a little bit at this
Yeah.
point.
Alibaba has deployed it at scale, but we're open sourcing it.
Right.
We're open sourcing it. We are creating this easy button for others to take, right?
Okay. Which license are you using for the open source?
It's SPDK BSD license. It's very permissive license.
The CSAL solution has 21 virtual volumes, and the TLC only has what, less than that? Is that? But they're both supporting like 10 gigabytes per second.
Yeah, basically, yes. Okay, so this 35% TCO gain is, again, only because of density, right? And we talked about other capabilities like RAID compression. As we bring on ZNS and FTP, we will gain that write amplification factor benefits, compression, etc. Over time, the idea is to add capabilities to CSAL and reference storage platform through the SPDK community to continue to drive that TCO down. So we have capabilities like we're working on CSAL's ZNS readiness, FTP readiness, RAID, multi-tenancy QoS is really important for cloud customers. A reference storage platform, this is one instantiation of it, which is a disaggregated NVMe or Fabrics target, but we can use more architectures like IPUs going forward to drive down the TCO of these reference storage platforms, etc. Okay, and then let's wrap up here. First, Solidym's P5810 provides a better cost performance endurance fit compared to Optane. We established that here, hopefully today. CSAL provides that easy button. It brings together this SLC drive with hyperdense QLC to enable those hyperdense QLC TCO benefits broadly. And then our reference storage platform, next step in that solutions approach, further enables that rapid development, assessment, and deployment of our continuing evolutions of like P5810 and P5336 will bring additional capabilities like ZNS, etc. And other players can also welcome to use this car, so to speak, as a solution to test drive their capabilities, etc., to drive the TCO down overall at the solution level.
So if you go back to the previous slide,
Yep.
As you continue to add those new features, do you actually have any idea of what the RAM and CPU cost would be of each one of those new features?
No, not off the top of my head, but a lot of these deployments, there are a variety of deployments. Of course, x86, you can sequester certain resources like vCPUs in memory. You can run it that way. There is also a push toward these new offload cards like IPUs, DPUs, etc.
Right.
So CSAL already runs, SPDK already runs on ARM cores and such. So we can always run on a card, etc. too, in a limited resource environment, etc. You will just run you have to scale it basically more cards, more CSAL instances, and we will bind to certain resources, and you will run so many CSAL instances inside the card, and then you scale out by replicating it
Okay.
based on your need.
I understand. It was just when you were showing the previous slide, you were showing that both the CPU and the RAM was quite a bit higher than the TLS.
Yeah, then TLC, because we are putting L2P in DRAM right now,
yeah.
but we can always turn the dial and do the paging method, right? So paging method is already working and available. We just, for this configuration, we didn't use it.
Okay. I was just curious.
Yeah.
Have you actually specifically talked to any DPU vendors, or you're just thinking you could put it in ARM if you wanted to?
So we have talked to DPU vendors, and they are running SPDK, and they naturally get CSAL as part of that, definitely.
Okay.
Could you consider CSAL a high availability solution? I mean, you mentioned multiple nodes. I mean, could you run CSAL software, multiple nodes of CSAL software to the same back end? I guess not.
No, it's a single node level solution. So
you can have it on
our
top
partner
of that
CSP,
someplace.
yes, so distributed, they can build distributed on top of this building block.
Right.
But we don't have distributed capabilities. So that comes to the integrators who want to integrate our SSDs with CSAL. They would have to develop that distributed capability.
Right. And the metadata replication across the SLC devices, there's triple replication. Is that how it works? Is that?
So we are talking about RAID 1, which is a mirror right now.
Only
two copies. But you could also, there are deployments that others are taking, like HA. We talked about HA, our partner, Starwind. They are replicating across nodes with HA, dual redundant or triple redundant. So again, it is that distributed thing, layer is above us. So you could do that node level redundancy implementations on your own, use this as a building block.
And the flash translation virtualization layer, is that, and that's being done by CSAL for the QLC or for the whole SLC QLC platform? I'm trying to understand where that, you mentioned you were paging, the flash translation layers back and forth into memory from the SSD.
So flash translation layer typically means you have a 4K block interface on top.
Yeah.
And then we have integrated caching and RAID in addition to being an FTL. Fundamentally, an FTL is, okay, any logical to physical, you have a mapping of 4K sectors to some physical underlying media, right? If it is ZNS, then you have to write sequentially. To large IU, you have to write in larger granularities, potentially sequentially, etc. Right? So that's the FTL functionality, how it is mapping that, adapting that any kind of interface that is more NAND-like ZNS is very NAND-like. NAND fundamentally underneath the covers is not like HDDs, like 4K block, right?
I know.
It's a flash, right? So that's flash translation layer that we have kind of moved up the totem pole here at the host level to kind of work with some of these flash-like emerging technologies like ZNS or FTP.
Like, I'm not sure what it's called. I guess it's called garbage collection. Those sorts of things that happen at the QLC layer, the SLC layer. Is that something that's
CSAL does it. CSAL will do garbage collection.
At your level?
Yes.
Rather than at the drive level?
That's why you see the write amplification factor 1 on QLC, 1 on SLC, but system level write amplification factor was about 2.3.
Right.
That was our write amplification factor. Because we are writing sequentially to QLC, and we are the one who's tracking what is valid, what is invalid in terms of mapping the 4K blocks to wherever we are placing. So over time, we get fragmented. We're going to defrag our drive with our GC algorithm. That's exactly what we are doing.
Okay. So you've turned off any of the SSD firmware that actually does mapping of the the blocks itself. Do you see any?
Pages. Yeah.
Yeah. Do you see any benefit in the read and write performance from doing that, or were those numbers that you gave at the beginning of the presentation with those mappings turned off?
So we are using standard P5336 drives with large IU granularity, so we don't take any read modify write penalty, but whatever is inside the SSD, it's the same SKU we are using with CSAL. There are opportunities now, as you're pointing out, we can start doing that, right? This is a better together kind of thing where we can simplify our SSDs. ZNS essentially does that. So as we move on to the ZNS, the CSAL is ready to fit in to do that sequentialization that is required by ZNS interface, for example.
Okay, because lots of times, like the SSDs will actually have an option that says you can turn off,
Garbage
write
collection.
leveling and garbage collection, that type of thing, and just we will take care of it. And lots of times you get a performance improvement out of that.
Yeah, so in this case, we are the one, CSAL layer is the one that is doing garbage collection. So it's kind of moving that from the SSD level, and we can hopefully do it more predictably we are at the host level. We have a little bit more intelligence compared to what SSD could do. SSD, the garbage collection will go off all of a sudden, and all of the SSD machinery gets tied up in that garbage collection.
Yeah.
So we can hopefully control that a little bit better to make it predictable performance, consistency, etc. That's the value prop of
And
CSAL.
typically when the WAF is hovering somewhere around 1, you don't see a lot of garbage collection really happening on an SSD, right? Typically when you have a very high WAF that is happening, and that's when you see the randomization of the data, and that's when you would see a garbage collection kicking in on a drive, right?
Right, and
right.
you said it's all one on those, so
Right, exactly, right.
Yeah.
Yeah. So that's an optimal way of, like, when they sequentially write the data to the QLC, that's the best way of writing to the QLC because you preserve the endurance of the drive.
Right, it is, yes.
Right. So SLC takes the beating in terms of the WAF, but again, even on the SLC, the WAF was turning out to be about one-ish.
Yeah.
Okay.